and sharing my screen. And so first of all, last class, we went through all sorts of things with quadratic equations. Homework 1.4 that's due today is on the complex numbers, and homework 1.5 on the quadratics is due on Monday. But over the weekend, there's going to be a quiz on complex numbers and quadratics. There'll be 4 quadratic equations. You're asked to solve one by factoring, one by using the square root property, one by completing the square, and one by using the quadratic formula. In addition, there are 4 problems dealing with complex numbers, multiplying complex numbers, dividing complex numbers, multiplying a conjugate pair, and rewriting an expression with negative radical underneath the radical, negative radicans as a complex number. Today we're going to look at other types of equations. That homework 1.6 will be due a week from today. I'm not sure if we're going to get through quite all of those other types of equations, but we should get through the lion's share of that section. Before we get started, does anybody have questions on any of that? Or does anybody want to look at any questions from any of the homeworks? No questions on any of the homework? Nobody wants to look at any of those problems?
Could we go over one more time about the 4 different formulas used for the imaginary numbers? I think it was.
We don't really have formulas for imaginary numbers. What we have to remember is that if we're adding, subtracting, multiplying, that imaginary numbers in a lot of ways behave like a variable, behave like x would. What you do have to remember is that you never leave an exponent on I. I to the first is just I. I to the second is -1. I apologize, my pen moved on me. I to the second is -1. I to the third is -I, and I to the fourth is 1. Past that, those powers repeat. If we're dividing complex numbers, let's say I have 4i over 6 plus 5i. Remember that we want to get that complex number out of the denominator, so we use the complex conjugate, which is like when we're multiplying by the sum and difference with binomials. Since this is 6 plus 5i, the conjugate would be 6 minus 5i. Because we're working with fractions, whatever we multiply the denominator by, we want to multiply the numerator by the same thing, because we want to just multiply by 1. In the numerator, we'll distribute and get 24i minus 20i squared. But we have to remember that I squared is -1. So that becomes 24i plus 20. And it's more standard to have the real part first. So we'll write that as 20 plus 24i. Because they're conjugates in the denominator, it's like, again, multiplying the sum and difference. It becomes the difference of the squares. So it becomes 6 squared minus 5i squared, which becomes 36 minus 25i squared. I squared is -1. So that becomes 36 plus 25, which is 61. And then to put it in standard form, we break it into 2 fractions. We've got the real part plus, with the imaginary part, we're going to take the ratio of the coefficient to the denominator and then pull that I out to the side. So in terms of complex numbers, that's in general. Otherwise, if we have something like simplify the square root of -75, that would be the square root of simplifying 75.
25 is a perfect square times 3, and because it's negative, we make it a factor of -1. The square root of 25 is 5. The square root of 3 is the square root of 3, and the square root of -1 is I. Is that what you were looking for, or were you looking more for examples of the different types of quadratic equations?
No, that's yeah, that's what I was looking for. I was also kind of looking for the different examples of the quadratic equations too.
Okay, well then let's look at a couple of problems with different types of quadratic equations. I don't feel like making them up, so I'm turning to a page in my textbook. Let's add a page for quadratics. Let's first solve by factoring. And let me look at something like 16x times x minus 2 equals 8x minus 25. And I'm going to ask for a little bit of help here. What should I do first?
Distribute.
Beautiful. So that gives me 16x squared minus 32x equals 8x minus 25. Then what?
Combine like terms.
Well, make one side 0. We don't really have like terms on either side to combine. We're going to bring everything over to that here. We bring it over to that left-hand side. And I think that's what you meant by combine like terms, yeah?
Yeah, that's how we used to say it when I was in high school.
So that's 16x squared minus 40x plus 25 equals 0. Whoops. Now we want to factor that. And I think for that 16x squared, if I have 4x and 4x, and for that 25, if I have 5 and 5, signs are the same, both minus. I think that'll give me that 40 in the middle. And then do you remember, because they multiply to 0, then one of the two of them has to equal 0. And when we solve those resulting equations, we get x equals 5/4. And the other equation is exactly the same. So we also get 5/4. So this one is one of those ones where it looks like there's only one answer, but really there's two answers and they're both the same. The solution set though, you'd only write that 5/4 once. Solving by factoring, all right.
Yeah, thank you.
Then next we had solved by using the square root property. An example might be something like x minus 1 quantity squared equals -9. And here it would make sense to use that square root property because I have something with a variable squared equaling a constant. So remember, we're going to take the square root of both sides. But that side with the constant has two roots, a positive and -1. On the variable side, because taking the square root is the inverse, the opposite of squaring, it has a net effect of just giving us that base that we were squaring. And the square root of -9 would be 3i, again, because it's negative. So here I'll add 1 to both sides. And I'll get x equals 1 plus or minus 3i. To write them in the solution set, it would be 1 plus 3i, 1 minus 3i. Is that one all right?
Yeah, that one's good. Can I just get a moment to copy the answer?
Let me know when you're ready and we'll look at solving one by completing the square and then solving
Good, thank you.
the quadratic formula. Completing the square. When we complete the square, what we want to try to do is we want to take an equation and gently nudge it into a form where we can use the square root property. We do that by making this perfect squared trinomial. Let's say I have, for example, x squared plus 6x plus 5. No, you know what? I'm changing my mind on that one. Let's say plus 13 equals 0. Again, first thing we want to do in completing the square is get that constant alone on one side. So this is the one method where we don't put it in standard form first, but rather we move the constant to the other side. And then we have to decide what value needs to be added at the end to make that a perfect square trinomial. And to reach that decision, we said we wanted to make sure we had a leading coefficient of 1, which we do. Remember, we said we look at that first degree term. We said that we take half of that coefficient and square it. So that would give me 3 squared or 9. So I'm going to add 9 to both sides, which would give me x squared plus 6x plus 9 equals -4. We did that so that that trinomial would be a binomial squared. That would be x plus 3 squared equals -4. So now we can use that square root property that we looked at in the preceding example. But we have to remember that constant side has 2 roots, a positive and a negative, which gives me x plus 3 equals plus or minus the square root of -4 would be 2i. And then when I subtract 3 from both sides, I get x equals -3 plus or minus 2i. We'd separate those into -3 plus 2i or -3 minus 2i. Does everybody remember that? Completing the square that we looked at last time. And that's a method that should work for solving any quadratic. Not going to lie, I probably would not use that if the leading coefficient were not 1. Or after I divided to clear the leading coefficient, that middle coefficient was not an even number. Because once you start getting into taking half of an odd number and square it, you start getting into fractions. And that can be a little involved. So let's look at what we could do in those cases. And so let's go through and let's solve using the quadratic formula. And let's look at 3x squared equals 2x minus 1. Now this one, does everybody remember, we do want to put it in standard form. So I'm going to subtract the 2x and add the 1 to both sides to get 3x squared minus 2x plus 1 equals 0. Now that it's in standard form, I want to look at just those coefficients. The coefficient on the second degree term is a. The coefficient on the first degree term is b. And the constant term is c. And then you need to remember that quadratic formula that x will equal -b plus or minus the root of b squared minus 4ac all over 2a. When we substitute in, we get then the negative of b is -2 plus or minus the square root of -2 squared minus 4 times 3 times 1 over 2 times 3. So that gives me, oops, I made my line a little bit too long. That gives me 2 plus or minus the square root of 4 minus 12 would be -8 over 6. Now that square root of -8, we want to simplify, and because it's negative, we know we're going to be getting complex numbers. So 8 we can think of as 4 times 2. And then again, because it's negative, we need that factor of -1. So that gives me 2. The square root of 4 is 2. The square root of 2 is the square root of 2. And the square root of -1 is I. So that gives me 2 plus or minus 2 radical 2i over 6. Let's separate the real part, 2 over 6, from the imaginary part, 2 radical 2 over 6 times I. And then let's reduce those fractions so that we get 1/3 plus or minus radical 2 over 3i. So as a solution set, we'd have 1/3 plus radical 2 over 3i. And we'd also have 1/3 minus radical 2 over 3i. Are you folks proficient in all 4 methods? Can you do them? Can you factor to solve using that zero multiplication property? One side 0, and then if the factor is multiplied to 0, you can set each factor to 0. That square root property, where we have a quantity involving a variable squared on one side and a constant on the other, then we can just take the square root of both sides. You just have to remember that that constant has 2 roots, a positive and a negative. Completing the square, we want to try to get our equation into that form where we have a perfect square equaling a constant. And we do that by creating a perfect square trinomial. Again, we have to add half of that middle term squared to get there. And then the quadratic formula came from doing that, completing a square to a general quadratic, which gave us a formula that we can just substitute into to find those solutions. I think the hardest part of the quadratic formula is remembering.
Hey, and speaking of that, can you just show the quadratic formula that you have above real quick so I can copy it down?
No, I'll tell you what, I'm going to ask you guys as a group to help me remember it. X equals, anybody? Negative
B
plus or minus the root of
B squared.
Squared minus 4ac.
minus 4ac, beautiful, all over
2a.
2a. X equals negative b plus or minus the root of b squared minus 4ac, all over 2a. Cool.
And you said that those are the 4 solutions we're gonna have to have for our quiz.
So your quiz is gonna be just like these 4 equations we did, one of each. And then just like on the other page, you're going to have to multiply complex numbers, divide complex numbers, and put an expression with negative radicands in terms of I.
Okay, thank you.
Can everybody do that?
A practice quiz for the quiz this weekend available on Blackboard.
A practice quiz?
I know sometimes there's like practices that you can take. I didn't know if there'd be one available for this quiz. Like
Usually practices are for tests. Tests are like 60% of your grade. They're a big deal. I haven't been putting in practices for quizzes because quizzes are just a very small part of your grade. And they're just looking to see if you can do the problems without the help functions. The questions from this quiz would probably, I don't know if they're exactly the same questions, but they would be questions from homework 1.4 and 1.5. So it would be like 4 questions from homework 1.4 and 4 questions from homework 1.5. And so again, those homeworks are probably the best practices.
Okay, thank you.
So it's like the homeworks are practice for the quizzes, but you've got help. The quizzes are practice for the tests, kind of seeing if you can do it without help in a kind of a low stakes, not really threatening, it doesn't, quizzes don't affect your average very much at all. They're like 10% of your grade. There's going to be enough quizzes because the practice tests count as quizzes that I'll drop the lowest 1 or 2. At most, a bad quiz will affect your average by maybe 0.5%. It's just practice for you to see if you can do it without the help functions before it becomes a high stakes test. So the quizzes are more for both you and me to see if you can manage the problems without the help functions before you get to a test. Okay.
Okay, thank you.
All right. Then if there's no questions on any of the homework problems, you guys are amazing me here. Not,
But thank you for going over those for those 4 equations.
no problems, at any point in time, you guys just have to ask. I can do whatever you need, but I'm not a mind reader, so thank you for asking. If there are none on the antique stuff, today we're going to start looking at solving other types of equations. And we're going to find that these make use of everything that went before. The first type of equation that we want to look at is a polynomial equation. With a degree higher than 2. Second degree are those quadratics, and we've beaten quadratics to death, pardon me. We've got 4 different ways of solving them. First degree are our linear equations, and we did those at the beginning of this chapter. And I'm guessing that everybody's kind of been proficient, maybe in a previous algebra class, at solving equations where there are no exponents. When we talk about higher than second degree, today we're going to start out by looking at equations that have exponents higher than 2. We're going to have 2 different methods of solving them. One we'll look at today at the beginning of this section, and the other we will look at probably on Tuesday because it's the end of the section. The first way that we're going to do this is to, just like we started with our quadratic equations, we're going to start by solving by factoring. And so if we start with an example, let's look at 2x cubed plus 3x squared equals 8x plus 12. And if we're going to solve it by factoring, we're going to be making use of that 0 multiplication property. And in order to use that 0 multiplication property, things have to multiply to 0. So we're going to start by make one side 0. We want to put the other side in descending order. Because remember when we were factoring, we had said it was easiest to factor if we had things in descending order. So as I look at this equation, I see that both sides are already descending order. I'm looking at the highest degree term, and usually you want to keep that highest degree term positive. We want to have a positive leading coefficient. And so here, I think would probably benefit most by if we try to make this right-hand side 0. So to make that side 0, I'll subtract 8x and 12 from both sides. On the right, I'll have 0. On the left, pardon me, I have 4 terms. They all have x, but because they're different degrees, almost all of them have x. I apologize, I overgeneralized. Because they're different degrees, they're not like terms, so we can't combine them. So I'm going to leave that as 2x cubed plus 3x squared minus 8x minus 12. And so now that we've got one side 0, on the other side, we want to factor completely. And remember from last unit, when we were looking at just factoring polynomials, if it says factored completely, factor as much as you can. Don't be surprised if you have to factor more than once. As I look at this equation, again, whenever I factor, I think we had said, whenever I factor, I say to myself, is there anything in common? Is there anything in common between 2x cubed, 3x squared, 8x, and 12? And I don't think so. After we looked for a common factor, we said we counted terms. This polynomial has 4 terms. We had a couple of tricks up our sleeves if there were 4 terms. Does anybody remember what was the first thing we tried to do if we were trying to factor a polynomial with 4 terms?
Wasn't it like you would do like 2x cubed would be 2x squared and then times 2x? Something like that? Or am I completely off?
We're going to do something like that, but do you remember with 4 terms, we try to do that factoring by grouping. I say 4 things are too much. I can't do 4 things at a time. So remember we split it up the middle? We said, what do those first 2 terms have in common? And here's where I think what you were saying comes into play. These 2 terms have a common factor of x squared. So that'll leave me with 2x plus 3. And then remember, then we looked at the back side. What do those 2 terms have in common? I think they're both negative. And what's the largest number that goes into both 8 and 12? 4. And when I divide that by -4, aren't I left with 2x plus 3? And you remember with this factoring by grouping, I'm keeping my fingers and toes. Folks, could you mute yourself if you're not talking to the class? Remember when we were factoring by grouping, if those 2 matched, it made us happy because now that's a common factor, 2x plus 3. And when I take out that common factor, I look at what's left are those coefficients x squared minus 4 equals 0. But then I say to myself, can I factor any more? 2x plus 3 is first degree. That's done. X squared minus 4. Does anybody notice that they're both perfect squares and it's subtraction in between? So can anybody remember how to factor x squared minus 4?
X minus 2, x plus 2.
Beautiful, x minus 2, x plus 2. And so now we've got all of these first degree terms multiplying to equal 0. So we're going to use the 0 multiplication property to set each factor equal to 0. Or the general idea that if those three things multiply to 0, the only way I can have a product of 0 is if one of those quantities that I'm multiplying is 0, and I don't know which one. So I'm going to say that it's possible that any one of them could be 0. Yeah, that's a 2. And so now we'll solve the resulting equations. So when I look at solving this first equation, trying to get the x alone, first we'll subtract 3 from both sides, get that x term alone. And then to get a leading coefficient of 1, we'll divide both sides by 2, and we get x equals negative 3/2. To solve that second equation, to get the x term alone, we'll add 2 to both sides, which gives me x equals 2. And the last equation, to get that x term alone, I'll subtract 2 from both sides. And that'll give me x equals negative 2. So here my solution set has 3 values, negative 3/2, 2, and negative 2. And we shouldn't be surprised that we have 3 solutions because it was third degree. And again, I think we had said previously that the degree of the polynomial equation tells us how many solutions to look for. So since this is third degree, we're looking for 3 solutions. Last step would be to, because you want to make sure you're getting them all right before you turn your paper in, you want to check all of them in the original. And usually with solving equations like this, by factoring, all 3 solutions should work. The only possibility where it wouldn't work is if we made a careless mistake somewhere along the line. Does anybody want to see this check worked out? Or are you folks all right if I'm lazy and skip the check on this one? Any questions on this problem? This is the approach we're going to take with these. If I have an exponent higher than 2, I'm going to make one side 0, put it in descending order, factor, set each factor equal to 0, and solve those equations. Here, factoring gave us all first degree equations. That's not always the case. Let's look at this next example, unless somebody has a question on this one. Are you guys all right? Okay, not hearing any complaints. I'm going to assume that everybody's okay. This time, let's look at 3x to the 4th equals 81x. Again, don't cut corners. Don't try to eliminate things. we want to make one side 0 and factor. So I'm looking at my highest degree term. It's the 3x to the 4th. It's positive. So I want to keep it positive. So I'll make the other side, the side with the 81x 0. So I'll subtract 81x from both sides. So that gives me 3x to the 4th minus 81x equals 0. It's descending order, one side 0. So now we're going to factor completely. When I factor completely, I always look for a common factor first. Does anybody see the common factor here?
You can take the 4th root or whatever that's called from
Um, I think you're overthinking it. Is there a number that goes into both 3 and 81 evenly?
I mean 3.
Yeah, and is there a variable that shows up in both of them?
X, yeah.
X to my common factor is 3x. We're just common factoring to start with. Don't try to work too hard. Dividing the first by the 3x gives me x to the 3rd. 81x divided by 3x would give me 27. So far, so good? Now, this one was carefully chosen. You'll probably see one like this in the homework, because now this binomial is subtraction, but they're not squares. But does everybody see I've got x to the 3rd? So I'm thinking these might be cubes. Is 27 a perfect cube? Is there a number to the 3rd power that gives me 27?
3.
Yep. So I'm going to look at this as 3x times x to the 3rd minus 3 to the 3rd. And does everybody remember, if I have, whoops, that's a 3rd, by the way, the difference of cubes, it factors into, the quantity, the difference of the quantities that I'm cubing. It'll be the first term, the first root squared. Then, because this is subtraction, I'm going to use the opposite sign. That'll be addition. I'm going to take the product of those two quantities, and then I'm going to add the root of the second term squared, which means we're going to keep our factor of 3x, because this is x to the 3rd minus 3 to the 3rd. We'll have a factor of x minus 3. And then we'll have a trinomial factor, x squared. Because we've got a minus here, it'll be a plus. Multiply those two quantities, 3x plus square that last one, 9. And when we looked at this formula for factoring the sum or difference of cubes, we said, as a rule, this last term is usually not factorable. So that's going to be as factored as far as we possibly can go. And again, if those three things multiply to 0, then one of the three must be 0. So I'm going to go ahead and set each of those factors equal to 0. Which gives me 3 other equations to solve. This first equation is first degree. It should only have one solution. If I divide both sides by 3, I get that x can equal 0. That one's not too bad. The second one is also first degree. If I go ahead and solve this one, by adding 3 to both sides, I get x equals 3. That's my second solution. This third one is second degree. So I might get 2 answers from this third factor. We already decided that it's probably not factorable. Since it's not factorable, we will probably either complete the square or use the quadratic formula. I'm thinking because that middle coefficient is odd, I'm probably going to use the quadratic formula to solve this. And I am tired of talking, so I'm going to shut up for a minute, walk around the house once, stretch my legs, and give you folks time to use the quadratic formula to solve that trinomial equation. Have fun. I'll be back in a minute.
I have a question, Ms. Torella.
Yeah.
So for the like doing all the work, could we like I'm just wondering, for doing the multiplication, everything, do we have to write everything out like one by one, or do we have to put every single one, if that makes sense? Like see how you're doing right now. Could I skip over the part and put the like actual numbers in, like 4 times 9, and then do the underneath for number 2, or do I have to do each step?
What if you want to maximize your possibility for partial credit, what I would look for, what I would give you credit for in terms of solving something with a quadratic equation, if that's what you're asking.
Yes.
Is
Sorry.
getting it in standard form.
Okay.
Second, I want to make sure that you identify your variables correctly.
Mhm.
Third, I want to see that you know the formula, that you wrote it out correctly. Fourth, I'd want to see that you substituted everything in the right place.
Okay.
Because, again, I know you can do some of this stuff in your head, but if you want to maximize partial credit, let's say, for example, you made a mistake in the formula. If you made a mistake in the formula, but you did everything else right, and I could see where that mistake was made, I'm more likely to give you partial credit than just seeing a wrong number.
Gotcha. Okay.
Or over here, if I can see that you correctly identified everything, but if you made a mistake and put A in for C or B in for A or something like that, if I can see that was where you went wrong, I'm more likely to be able to give you partial credit than if I just see wrong numbers. Do you know what I'm
Gotcha.
saying?
I
And
know
so,
what you're saying.
I know that, like, if you were doing this on your own or for the homework, you know, you might kind of cut corners and not write all this out. Personally, when I do this album on my own, I cut corners and don't write it all out. But
Okay.
for something like a test or quiz, the more you can put on paper, if I can see that, oh my God, it was a careless mistake, and instead of substituting in 3, she substituted in -3 because her penmanship was bad, you know, I can give you
Sounds like
more
me.
credit than if I just have wrong numbers. So,
Okay.
yeah, I know all the writing's a pain in the ass. And so, if you don't have to do it when you're solving a problem on your own, great. But if you're taking a test or quiz, the more I can see what went through your head by looking at your paper, the more chances you have for getting partial credit. Does that make sense?
Okay. That makes total sense. Sorry about that. Just wondering, but no, thank
Oh,
you.
don't apologize. That's a very good question to ask. And so
Okay,
this would give
awesome.
me -3 plus or minus the square root of, that turns out to be -27/2.
Mm,
And then the square root of -27 turns out to be 3 radical 3i/2. And so that gives me my other two solutions are -3/2 plus 3 radical 3/2i, or -3/2 minus 3 radical 3/2i. And
Okay,
so,
thank you so much. Sorry, I just was wondering.
and no, you know what? Thank you, because I know sometimes people think math teachers are little dictators, and if I don't write it
Oh, no,
exactly
no,
right,
no, no,
and
no.
it's not that at all. I just want to, first of all, make sure you're doing the work and not yet just using a crappy app to get the
Yeah.
answers.
Yeah.
And second, I want to, the more you show me, the easier it is for me to justify giving you partial credit, even if your answers are all wrong. So,
Okay, gotcha. Thank you
Okay.
so much.
I'm trying to help you a little bit.
No,
So-
I appreciate it.
Did everybody get those two answers from that quadratic formula after I went on my rant? And again, this was fourth degree, so 4 answers shouldn't be a surprise. I'm going to ask you folks to do one more, and I'm going to just shut up and have you folks do it. Then we'll go on and look at a different type of equation. So last example, and this one isn't quite as involved as the preceding. I've got 4x to the 4th is equal to 12x squared. So again, make one side 0, factor, set each factor equal to 0. Are we ready to go over or not yet?
Did everybody get 0, radical 3, and negative radical 3? What I want to point out with this one is that what the hell happened? There are 3 answers, but I was 4th degree. If it's 4th degree, shouldn't I expect 4 answers?
Is it because the 1x turned into 0? So
Well, actually, that, you know how over here when we had x squared equals 3, we had to take both roots of 3, a positive and a negative? Over here, when we have x squared equals 0, technically we're taking the root of both sides and we get plus or minus a 0, which means we have 2 zeros. Over here, since x squared was equal to 0, it tells me that we actually have 2 roots that equal 0. And so 0 is a solution twice. And so that's why we say the largest number of solutions would be 4. You might have less than 4 if some of them are the same. How fun is that? Pretty cool. How'd you guys do with this one?
good.
Good. All right. Then this stage of the game, in order to solve a higher degree equation, we're going to make one side 0 and factor. The second type of equation that we're going to look at today are radical equations. And we're going to look at radical equations. Today we're going to just focus on one type where they're square roots. And to be considered a radical equation, the variable is in the radicand. We're going to consider 2 types of radical equations. The first type that we're going to consider are equations with 1 radical. Later on today, we'll look at equations with 2 radicals, and we'll see that they're twice as fun. So, we're looking at equations that have square root with a variable in the radicand. So we might have something like 2 times the square root of 20 minus 8x. Then outside the radical, minus 2x equals 0. How fun does that look? When we solve an equation that looks like this, the first thing that we want to do is we want to isolate the radical. And again, that's a fancy pants way of saying get the square root alone on one side of the equation. So to get the radical alone, to get that term alone on one side, first I'll try to get the entire term alone, which means I want to move that minus 2x, so I'll add 2x to both sides. That gives me 2 times the square root of 20 minus 8x is equal to 2x. Now that radical term is alone, but the radical isn't quite all alone. It's got that coefficient of 2. So I'm going to go ahead and I'm going to divide both sides by 2. And so now I've got that radical all alone. 20 minus 8x is equal to x. Now, in order to solve this equation, doesn't make sense that we want to try to get x out of the square root. And the way we're going to get x out of the square root, but only after the square root is alone on one side of the equation, is we're going to square both sides. Of the equation. So for the people who aren't in class, I'm going to just rewrite the equation as it is and go through and show that I'm taking both sides and squaring it. I'm doing the same thing to both sides, so it should be cool, but it isn't always. And so we're going to find that with these equations, the check is super important. But I digress. Is everybody all right when I square a radical because they're opposite operations, taking the square root and squaring? That has the effect of taking the radicand out of the radical, or as I like to say when I teach this concept in a foundations class, when you square a radical, it's just like taking the hat off. And so I get 20 minus 8x is equal to, on the other side, x squared. And now we've got an equation without a radical, which we're going to solve. So let's solve the resulting equation. And does everybody notice that this equation is second degree? It's a quadratic. So we need to put it in standard form. So let me subtract the 20 from both sides and add the 8x to both sides. And rewriting that in descending order gives me x squared plus 8x minus 20 equals 0. Got several ways of solving these. I'm looking at this one and I'm looking at those numbers, and I think this one should be an easy factor. X squared is x times x. 20 is 10 times 2. I want different signs. If I make a positive 10 and a negative 2, that'll give me that positive 8 in the middle. Now, if those multiply to 0, either the x plus 10 is 0 or the x minus 2 is 0. And so solving, I get that x can equal negative 10, or here, adding 2 to both sides, I get that x could equal 2. With these, it's super important. You must check in the original. With these, with the quadratic equations, we were a little lax with the checks, because again, the only time you're not going to get something to check is if you made an arithmetic error. But with these, it's really important to check, because sometimes you can do everything right and get a solution that works for your derived equation that doesn't work for your original equation. You get something they're called extraneous roots. Roots that work for the derived equation, the equation that you came up with, but don't work in the original. So going to my original, it was 2 times the square root of 20 minus 8x minus 2x equals 0. And if I check with x equals negative 10, that gives me 2 times the square root of 20 minus 8 times negative 10 minus 2 times negative 10. And I want to know, does that equal 0? Well, that's 2 times the square root of, I think the arithmetic in the middle would give me 100. plus 20, which gives me 20 plus 20, or 40. Does 40 equal 0? No. So this one we're going to reject. So let's hope our other answer works. If x equals 2, substituting into the original, I get 2 times the square root of 20 minus 8 times 2 minus 2 times 2. Does that equal 0? Well, that gives me 2 times the square root of 20 minus 16 is 4, minus 4. So that's 2 times 2 minus 4, or 4 minus 4, or 0 equals 0, and it checks. And so my only viable solution is x equals 2. And again, this comes because what we did was we squared both sides. And we're doing the same thing to both the sides of the equation. But, we're not exactly using that multiplication of property of equality. And so we can get these extraneous roots. Questions on this one? Should we try some more? Let's look at another example. Let's look at x minus the square root of x plus 11 equals 1. And again, with these, what we want to do first is get that radical alone. So let's subtract x from both sides. That gives me the negative of the square root of x plus 11 equals negative x plus 1. Again, just to make it look nicer, the radical has a coefficient of negative 1. Let's divide both sides by negative 1. So I get that the square root of x plus 1 is equal to x minus 1.
Should be the x plus 11, right?
Thank you. That's what happens when I take my glasses off. Sorry about that. I'm going to make excuses for myself. And so now we're going to go through and square both sides. This one's a little bit more involved than the last one. Yet on the left-hand side, because we're squaring the radical, we just take its head off, and we're left with the x plus 11. But over here, we're squaring a binomial. Remember, when you square a binomial, you can either think of taking that binomial and multiplying it by itself, or now that we've completed the square, maybe that pattern makes a little bit more sense. It's the first term squared minus twice the product plus the last one squared. Again, if that pattern doesn't work for you, feel comfortable to feel free to take the time to FOIL that out, multiply that out, or box it out, or distribute it out, whatever works for you. Again, now we've got a quadratic. Let's put it in standard form by subtracting x and 11 from both sides. Gives me 0 equals x squared minus 3x minus 10. And I think that's a relatively easy factor. Again, though, if you don't like factoring at this stage of the game, you could still use your quadratic formula. But I'm going to factor x squared is x times x. For that 10, I'm going to use 5 times 2. The signs are different. I think if I make the 5 negative and the 2 positive, it'll give me that -3 in the middle. Setting each factor to 0, using that 0 multiplication property, I get that x could equal 5 or x could equal -2. But again, with these, the checks are really, really, really super important. So I'm not going to ever blow off the check for a radical equation. For a radical equation, I'm going to do that check absolutely every time. And so if x equals 5, I get 5 minus the square root of 5 plus 11. And I want to know, does that equal 1? So that's 5 minus the square root of 16, or 5 minus 4 equals 1, and it checks. So this one's good. Now let me check and see what happens when x equals -2. I get -2 minus the square root of -2 plus 11. Does that equal 1? That's -2 minus the square root of 9. -2 minus 3 would be -5, which is definitely not 1. So this one we're going to reject. And so if there's one radical, we want to get that radical alone and square both sides. Can we do this, folks? Any questions? Can you guys hear me?
Loud and clear.
Okay, all right. Then they get a little dicier if a radical equation contains 2 radicals. And the fact that it has 2 radicals means we're going to have to square it twice. So what's that look like? Let's look at an example. Let's look at the square root of x plus 5 minus the square root of x minus 3 equals 2. Again, because there's 2 radicals, we're going to have to square twice. Over on the left-hand side, this is a binomial. And if I tried to square that, it would get ugly. That middle term would get a little frightening. So what I want to do first is I want to isolate one of the radicals. Just want to get one of them alone. So being over here, the first one's positive. Let me add that second radical to both sides. And that gives me the square root of x plus 5 is equal to 2 plus the square root of x minus 3. So far, so good?
Yep.
So now what we're going to do is we're going to square both sides carefully. So we're going to take that square root of x plus 5 and square it. And we're going to take that 2 plus the square root of x minus 3 and square it. On the left, it's pretty easy peasy. I'm squaring a radical. They're inverse operations. They undo each other. It takes the hat off the radical. I'm left with x plus 5. On the right-hand side, though, does everybody see that what I've got here are two terms? There's that plus sign in the middle. And so I have to think of taking that expression, 2 plus the square root of x minus 3, and multiplying it by itself twice. And in order to do that multiplication, I need to distribute twice, or box, or FOIL. I'm a FOILer. I think I've told you guys that a million times. First, 2 times 2 is 4. Outer, 2 times the square root is 2 times the square root. Inner, the square root times 2 would give me 2 times the square root. Last, the square root times itself would be squaring the square root, and that just leaves me with the x minus 3. So combining like terms, 4 minus 3 is 1, plus I have that term of x, plus when I take those radicals, they're like radicals, I can add them. 4 times the square root of x minus 3. And that equals on the other side x plus 5. And now this equation looks like the ones we did on the preceding page. So let's go ahead and do what we did there. Let's isolate the remaining radical. So I want to get this square root alone. Let me subtract 1 from both sides and x from both sides. Gives me 4 equals 4 times the square root of x minus 3. The radical term is alone, but it's got that coefficient. So let's divide both sides by that coefficient of 4. Gives me 1 equals the square root of x minus 3. Now we've got that alone. Let's square both sides again. You know what? I apologize. I want to rewrite that line before I square it. Gives me 1 equals x minus 3. And now we can solve. Let's add the 3 to both sides. Gives me 4 equals x. And again, with these, I really do want to check. We've only got one solution, so we're hoping that it works. But I want to just shrink this for a minute and look at the big picture. And as I look at the big picture, we did a heck of a lot of stuff to this equation. We did so much stuff that if for no other reason, I want to do a check to make sure that somewhere in all of the details there, I didn't make a careless mistake. So when I check, my original was the square root of x plus 5 minus the square root of x minus 3 equals 2. And if x equals 4, that gives me the square root of 4 plus 5 minus the square root of 4 minus 3, which is the square root of 9 minus the square root of 1, which is 3 minus 1 equals 2. So yay, we did it. And there's my solution. These ones are a little time consuming, would you say? I do believe that there is only one of these on the homework. Should we try another to make sure we've got it? Or do you think you have it?
Can we try another?
Sure. And let's have you guys try this one. Let's look at the square root of x minus 5 minus the square root of x minus 8 equals 3. And I'm going to let you folks do this one. Just while you're doing that, in case you're wondering, I'm just double checking to make sure that there is indeed only one of these in the homework, that I'm not being a liar. Then we'll go over. I lied, there are 2 in the homework. Did anybody else get that this equation has no solutions?
I did. Thought I was wrong at first, but
No, no. When I looked at the ones in the textbook, I looked for one that didn't look too terribly complicated. And I saw that they said the solution was the empty set. And I thought, it would be good for you guys to see one with no solutions. So there you go. Did anybody have problems working through all of this? Again, get one of the radicals alone, square both sides. And this is where they get a little ugly. When I square the binomial side, I need to think of multiplying it by itself or using the method of squaring a binomial, which gives me an equation that still has a radical left. Get that radical alone, square both sides, solve. But again, with these, the checks are super important. When we square both sides, we, could get those extraneous roots. So if these are all right, then there's two more types of equations to look at. I think we only have time to look at one of them, and they're really fun because it goes back to something that we looked at last unit that I think everybody found to be a blast. We're going to look at equations with rational exponents. And hopefully everybody looks at the word rational and sees inside it the word ratio, which reminds me that I'm talking about exponents that are fractions. And so, as a quick reminder, does everybody remember? A couple of things I want you to remember. Oh, Lord. How do you spell remember? If I have something to a fractional exponent, does everybody remember when a fraction is an exponent, it means I'm going to take a radical. My base is my radicand. The denominator is the index of the radical, and the numerator becomes an exponent. So for example, if I take 16 to the 3/4, it means I'm taking the 4th root of 16 and cubing it. The 4th root of 16 is 2. 2 to the 3rd is 8. Does that look vaguely familiar? Wasn't that long ago? We did it this semester. Another thing that I want you to remember, second time I misspelt remember, I'm on a roll, you guys. If I have something raised to a power and I raise it to another power, does everybody remember when we raise a power to a power, we multiply exponents? Third thing I want you to remember is when I take something and multiply it by its reciprocal, I get 1. So all of that
at the tip of your tongues, at the top of your head, things we're going to make use of right now. So to solve an equation with a rational exponent, let's start sort of simple. Let's say I have x to the 3 halves plus 3 equals 30. First thing that I want to do is I want to isolate the term with a rational exponent. Okay, so here, that's the x to the 3 halves. So I want to get that x term alone. I'll subtract 3 from both sides, and I'll get x to the 3 halves equals 27. So far, so good. Now, when I am done, I want to say that x is equal to some single quantity. And in order to get that x alone is x to the first. And so this is where I need that idea of reciprocals and raising a power to a power. What I'm going to do is I am going to raise both sides. What I do to one side of an equation, I have to do to the other, to the reciprocal power. So where I have x to the 3 halves equals 27, my exponent is 3 halves, the reciprocal is 2/3. So I'm going to go ahead and raise both sides to the 2/3 power. Well, we remembered that when we raise a power to a power, we multiply those exponents. And when I multiply something by its reciprocal, I get 1. So bam, I did it. I've got x to the first. Now on the other side, when I take 27 to the 2/3, because that exponent is a fraction, I'm thinking of taking a radical. My radicand is 27. My index is 3. And then I'm going to exponent 2 square that. Well, we said earlier today when we were looking at factoring the difference of cubes that the cube root of 27 is 3 and 3 squared is 9. And in an ideal world, I would love it if everybody was comfortable going from 27 to the 2/3 to the 9 using that definition of the fractional exponent and simplifying. Did I show you guys earlier, if your number skills aren't that great, if your number skills, you can't look at 27 and see that that's 3 to the 3rd, that you can take 27 to the 2/3 power with a calculator. Did we talk through that previously?
I
Yeah,
don't
we did.
remember. If we could go over it again, that'd be cool.
Okay, so I've got x equals 9, where I had 27 to the 2/3. In order to do that with a calculator, I'd type in my 27. I'd use my caret up or whatever key you need to get an exponent. But because that exponent is a fraction, I want to put it in parentheses. My exponent is 2/3, so I'm going to take 2 and divide it by 3,
close the parentheses and hit equals. I have a tendency to treat all fractions as a division problem when I use my calculator. Some of you might instead of taking that 2/3 and writing it as 2 divided by 3, you might be comfortable with that fraction key. Both results should give you the 9. Did everybody get the 9?
Yep.
Okay. Now here's the dealio. We raised both sides to a reciprocal power. That's kind of like with the last equations where we squared both sides. So with these, I would also make sure to check. So checking x to the 3/2 plus 3 has to equal 30. So if I take 9 to the 3/2 plus 3, well, 9 to the 3/2 is the square root of 9 cubed. So that's 3 cubed or 27 plus 3 equals 30, and it checks. But I'm guessing that these probably can get a little bit more complicated. So let's look at a more complicated example, unless somebody still has a question on this one. Not hearing any? Let's look at x plus 5 to the 2/3 minus 4 equals 0. So again, we want to get that part with the rational exponent alone. So I'm going to add 4 to both sides. That gives me x plus 5 to the 2/3 equals 4. And then to get rid of that rational exponent, I'll raise both sides to the reciprocal power. On the left, when I raise a power to a power, I multiply those exponents. And when I multiply reciprocals, I get 1. So this just leaves me with x plus 5 equals, well, on the right-hand side, that 4 to the 3/2, it's a fraction, so I'm making a radical. I'm taking the square root of 4 and cubing it. The square root of 4 is 2 to the 3rd is 8. And so now when I solve, I'll subtract 5 from both sides and get x equals 3. If I go ahead and check, I'm looking at 3 plus 5 to the 2/3 minus 4, and I'm hoping that equals 0. So if I take 8 to the 2/3 minus 4, again, when I have that number with a fractional exponent, it means I'm taking a radical. The denominator is 3, so I'm taking the cube root of 3 and squaring it. I'm sorry, the denominator is 3, so I'm taking the cube root of 8. I apologize, I misspoke. I'm so sorry, you guys. The cube root of 8 is 2 squared is 4 minus 4 equals 0. So it checks. Next one's a little bit dicier. Is everybody okay with this one? Next one, we've got to keep our minds open a little bit. If I look at x minus 4 to the 2/3 equals 16. Here, I've got that piece with the rational exponent alone. So I'm going to take both sides and raise them to the reciprocal power for the 3/2. When I raise a power to a power, I multiply exponents. And reciprocals multiply to 1. So I get x minus 4. But now over here, when I take the 16 to the 3/2, I get the square root of 16 cubed. But that square root, there's two of them, a positive and a negative. And so I get 4 cubed or negative 4 cubed. And so I get x minus 4 equals 64, or x minus 4 equals negative 64. Adding 4 to both sides, I get x equals 68, or I get x equals negative 68. So when we check,
Wouldn't it be negative 60 on that right side? 'Cause you're adding 4.
yes,
to the
it would. Thank you. Just looking to see if you're awake. So if I check when x equals 68, 68 minus 4 to the 2/3, does that equal 16? Well, that's 64 to the 2/3, or the cube root of 64 squared, or 4 squared equals 16, and it checks. If I check x equals negative 60, negative 60 minus 4 to the 2/3, does that equal 16? Well, that's negative 64 to the 2/3. So that's the cube root of negative 64 squared, which would be negative 4 squared, which is still 16. So it also checks. How fun is that? I'm going to give you folks one more to try on your own. And then we'll, I guess we'll call it a day. Any questions on this one before we go on?
I have a question. Why do we do plus minus square root of 16?
Because 16 has two square roots, a positive one and a negative one.
Okay, thank you.
Okay? Remember when we use that square root property, when we take a square root of a number, we have to remember that they have both positive and negative.
All right.
So let's have you folks try, oh, I'm just picking a random one out of this textbook that's in front of me. Trying to pick a pretty one. Let's look at, oh, my eyes are so bad. 8x to the 5/3 minus 24 equals 0. Real quick, double checking attendance while you guys are working. Aubrey, I did not see come in. Sam, I did not see come in. Kaya? Is Kaya here? Alyssa, you're here, yes?
Yep, I'm here.
Martin, you're here? Uh, oh. Bailey, I saw, but I don't still see him. Dana? Jason? Kat? Jason, you're here?
Yeah.
I thought I saw you previously, and then when I was just scrolling through the gallery, I didn't see you. Okay, sorry about that, Jason.
That's all right.
Okay. All right. Then, did everybody get the 5th root of 27, or at least 3 to the 3/5? Yes or no? When we had something to a fractional exponent, we said that the denominator is the index, and whoops, the numerator is the exponent. And you can write it either the exponent after you take the root or the exponent before you take the root. And over here, because the 3 to the 3/5 is an irrational number, we're going to leave it in radical form. And so it's more normal with this to use that second option. Usually when I'm doing computation, I find it, the numbers are smaller if you first take the root and then raise it to a power. But every once in a while, you need to do that exponent first. But So anyways, today we covered a lot of territory, right? We looked at equations with exponents higher than 2. And we said with those, we're going to make one side 0 factor and set each factor equal to 0. And we said that that highest exponent, that degree of the equation, is how many solutions we should look for. Then we looked at radical equations and we said get the radical alone and then square both sides. And with those, the checks are super important. Then we also said if we have an equations with fractional exponents, we want to make sure that we get that piece with a fractional exponent alone on one side and then raise both sides to the reciprocal power. So I think I adjusted attendance. I'm going to